Today I'd like to talk to you about a number of new indirect manufacturing applications that you can achieve using MultiJet 3D printing technology, and in particular based around the ProJet MJP 2500 Plus 3D printing system from 3D Systems. Along the way, we'll also review a little bit of the basics about this technology and then get into those indirect manufacturing applications. Before we dive in, a quick introduction. My name is Sam Green. I'm the Global Category Manager for the professional line of 3D printers here at 3D Systems. I've been involved in the additive manufacturing industry now for about 10 years with some of the leading 3D printing technologies and solution providers. For those of you not yet too familiar with MJP technology, I've tried to summarize here the main benefits and will elaborate on some of these points shortly. But in a nutshell, MJP technology delivers highly accurate parts with the finest design details that I've seen from jetting technology over the years. Any printer is only as good as the materials and the 3D parts that come out of it. So material development is key, and 3D Systems is constantly working to introduce new advanced engineering materials that open new application possibilities for manufacturers, designers, and engineers. Unlike other technologies, MJP is ideal for producing moving assemblies straight out of the printer and for lightweighting heavy parts. You can simulate glass or PMMA with a range of clear transparent materials, and functionally you can simulate snap fits, hinges, and create very strong jigs and fixtures. The parts are large enough to fit a good majority of industry applications, and lastly, the MJP system is fast, reliable, with a 24/7 uptime, and is a system that today is used by thousands of design and manufacturing companies in virtually every manufacturing industry in the world. Now let's look at some of those points in more detail, and later we'll see how to tie those into our indirect manufacturing applications. So we mentioned that MJP delivers the finest design details. What's so special about MJP technology in this regard? MJP stands for MultiJet printing, which uses inkjet print heads to jet an acrylic-based resin that's cured by UV light on the build tray. This uses proprietary thermally controlled materials. As each heated droplet of material is jetted, it immediately cools and holds its shape as it lands on the part or support surface. Now, this is not necessarily the case with other resin 3D printers. With MJP, the material does not ooze over edges or pull in corners. The edges are 90 degrees sharp, the holes are round, corners are clean, and sidewalls have excellent overall quality. Now combine that information to the actual printer resolution. ProJet MJP 2500 systems print at 800 by 900 by 790 dpi at 32 micron layers. Just for comparison, the human eye or the human retina has a limit of only 300 dpi. Combine this to the accuracy of plus or minus 0.001 to 0.002 inch per inch of the actual part dimension. And you see here the result in this comparison between MJP and a competitor. You see the holes on this shower nozzle in the top photo are perfectly triangular all the way up to the tiny tips, while the competitor's tips are sealed and closed off. The result is that you see the spray of water coming out of the MJP nozzle straight and clean, while for the other competitive system it's very skewed, a nice indication of overall resolution here. Another factor responsible for delivering fine design details, something that is often overlooked, is the support material. This is where jetting technology differs from other technologies such as SLA or DLP or FDM. Jetting technology allows you to separately jet a model material and a differently formulated support material. MJP technology has really perfected this process by jetting a support wax that is easily dissolved away in a hands-free process that also does not use dangerous chemicals. This process takes care of the very fine details of your part, and because we're not using heavy chemical-based solvents or high-pressure water jets, there's no damage or deformation to the part, and no residual support material is left trapped in the cavities, as you see with the alternative system in the bottom photo here. And here's a typical part that I've printed and filmed for you in my own hand. You see the holes on this filtration device are clean of support and sharp, unlike other jetting technologies, and the curved surface is smooth, without the stepping effects you typically get from even high-end FDM printers. As I mentioned, we're constantly working to improve and expand the material possibilities available on the MJP platforms. To date, we have a range of general-purpose materials in white, clear, and grey. These feature rigid functionality with a moderate flex and the look and feel of injection molded plastics for typical prototyping applications. The M2R clear and white are actually Class 6 capable for medical, biocompatible, and skin touch applications, while the tan material is a really high quality, high contrast material with good modulus and a heat resistance up to 71 degrees C. The M2R black material exhibits high rigidity and low flex, as well as higher temperature resistance and an opaque black finish. The VisiJet Armor engineering clear material exhibits an exceptional mix of tensile strength and flex, delivering advanced prototyping performance for many applications, as we will see shortly. The VisiJet ProFlex material exhibits high impact resistance and polypropylene-like performance. This is ideal for living hinge applications and use cases that require durability and extreme pliability, while the elastomeric black and natural materials are excellent for printing soft, rubber-like parts such as gaskets, piping, and some molding applications. In these two GIFs, I've printed a couple of nice parts for you. The left part is printed in the M2R rigid black material. What's great here is that this part features a functional screw thread assembly that came like this out of the printer, thanks to the melt-away support and the high fidelity and resolution of the printer itself. The clip on the right is printed in the tan material, and again, this was printed as a finished assembly, showing smoothly working, accurately printed and fine detailed joints and hinges. Again, both these parts are ideally to be printed in MJP technology, both in terms of the moving parts, the complexity, and the final quality of the parts themselves. Okay, in this slide, you get the pleasure of seeing me in person. So here I am, I printed one of my favorite parts, and this is a really unique capability to MJP technology. This is a prototype for a commercial drone. Using our proprietary 3D Sprint software package, you can quickly and automatically create a sparse, hollow structure within your part. And with the melt-away support and some cleverly located drainage holes, you can end up with a part that's up to 70% lighter. And of course, when you're using less material, you cut your cost per part down, in this case by up to 35%. Another important feature of MJP technology is the ability to produce really clear, transparent, yet functional parts using a choice of two different clear materials. The M2R clear, which as I mentioned a few slides back, is biocompatible Class 6, which makes this a great choice for medical devices when you need skin or mucosal membrane contacts and where you need to see through the parts, such as in surgical guides or devices where liquid or gas flow is flowing through a system. The second material here is the VisiJet Armor, which is really good as a functional material with high impact resistance that makes this ideal for simulating clear transparent parts as part of a general or larger assembly, such as in automotive lighting, covers, and electrical or consumer goods products. These parts can be tinted with regular fabric dyes to create a nice selection of clear colored parts. Out of the printer, the clarity can be easily achieved using lacquer or sanding or a combination of both. MJP technology is also an excellent way to iteratively test complex and fine detailed snap fit designs. So the VisiJet Armor and ProFlex materials were specifically designed to create robust snap fits, simulating the properties of traditionally injected molded plastics, as you see in this photo and this short GIF. The rigid material is also extremely versatile for when you need to drill, tap holes, press fit precision dowel pins, add screws to bosses, press fit brass inserts, and machine precision holes. In addition, you can also print those screw threads directly into the part. The unique capability of MJP allows it to easily print most thread sizes, which can be used in combination with standard threaded machine screws. In this slide, we have a stop motion comparing MJP 2500 Plus on the left with another jetting system on the right. Both have the same parts on the tray, yet the 2500 plus system finishes the same job in 1/3 of the time. In fact, there are many jobs where it's just as quick or nearly as quick to produce multiple parts as it is to produce just one. That's because the print head runs along 3 lanes, and if you're able to stack your parts or nest them nicely within a single lane, you can become far more productive on large or recurring jobs. In fact, with a print speed of 303 centimeters cubed per hour, or 18.5 inches cubed per hour, most practical jobs will be finished in one day or overnight. Add to that the time and labor saved with the soluble support post-processing as I've described earlier, and the fast, easy job submission with the 3D Sprint software, and you'll be overall extremely fast and efficient. So that's a brief summary of the benefits of MJP technology. For the start of 2020, we've added some unique material capabilities that open some new and very exciting applications, both for prototyping and manufacturing, particularly with the use of 3D printing for indirect production parts. Essentially, that means you can now short-circuit the expense and time required to make tools that are used within the traditional manufacturing workflow, and now you can make them faster and more cost-effectively. Indirect manufacturing contrasts with direct production parts, where a 3D printer would be used to totally replace the traditional manufacturing setup and workflow. To be clear, that's not what we're discussing here, and that's a discussion for another time. Back at the recent Formnext show in 2019, we introduced a new breakthrough in engineering materials with the M2S HT-90 material. This is the first in a new line of advanced specialty materials. So what's so special about the HT-90? Well, it combines 4 really useful properties and features within a single material. Firstly, water clear transparency for when you need a material that looks like Perspex or glass. This is great when you need to view a liquid or a gas flow within the material, or when you're trying to align a part over holes or screws. Second, it has a heat deflection temperature of 90 degrees C out of the printer, with no additional post-thermal cure required, which would be typical in other jetting resin printers. Third, the HT-90 is printed in a new ultra-high definition printing mode that promises even sharper planes, corners, edges, and details with virtually no appearance of build lines on the part. The high HDT of this material, combined with the high sharpness and fidelity of the parts, makes it really suitable for a range of tooling needs where hot plastics are injected inside or metal is pressed onto a 3D printed surface, as I will show you shortly. And fourth, the material features USP Class 6 biocompatibility for skin contact and mucosal membrane contact, making it ideal for medical devices or medical planning, as well as a range of parts that have to be worn on the skin. So how do those benefits translate into the traditional manufacturing world? Well, I've listed here just an initial sample of what those potential applications could be. The message I want to get across here is that there may be quite a few more specific to your unique business or industry workflow. My intention here is that you see these examples and then start to generate ideas and find ways to apply the same 3D printing benefits to your own manufacturing setup. So let's take a look at some of these in a bit more detail. First up is thermoforming. This is one of those manufacturing processes that intuitively can benefit from 3D printing. The process consists of heating a thermoplastic material to a pliable temperature and then stretching it onto a molded shape. Using 3D printing for thermoforming the molded shape saves time and allows designers and engineers to quickly and easily fabricate more complex designs that would be quite difficult and require a CNC machine expert as well as your CAD designer. 3D printed dies are faster to generate and cheaper compared to traditionally manufactured parts, and yet they can be used to form tens to hundreds or even thousands of parts, depending on the specific design. Using the new HT-90 material is ideal for most thermoforming applications. The 3D printed dies or tools can be used to replace either the entire machined die or just a small part of the die with the use of an insert. The 90 degrees HDT provides a good thermal resistance to the hot plastic that contacts the tool. There's virtually no degradation to the tool during the process, and the 3D printed parts provide a good cycle time for most geometries. Thanks to the fine feature definition of the MJP printing process, you get over 1.1 billion drops of material per cubic inch of part volume, which means you get extremely accurate and fine resolution die or mold surfaces. Another great benefit of the MJP process is that the melt-away support material that we discussed earlier allows you to easily create porous lattice structures and tiny venting holes for the vacuuming of the final plastic. In the example in the photos you see here, the top photo shows you a mold die printed in the HT-90 material. From this part, 400 plastic parts were generated, 100 from each tool, with no noticeable degradation to the quality of those parts. The HT-90 material's elongation of break of 4 to 9% also provides just enough flexibility to allow for the removal of the final formed parts without damaging the tool or destroying small features on the die surface. All in all, the use of a 3D printed tool or die saves anywhere between 3 to 10 times the cost and time of traditional low volume tooling. When it comes to the injection molding process, using MJP technology with a new HT-90 material can similarly save you between 3 and 10 times the time and cost of traditional metal tooling. 3D printing in this case can be used in 3 different ways. First, for churning out fast production plastic injection mold tools for low volume jobs. Secondly, for creating unique high value inserts that sit inside your traditional molding tool plates. And thirdly, for prototyping and thereby assisting in the development of the traditional metal tools. Iterative testing of metal tools can take weeks or months, so 3D printing allows designers to go through multiple design cycles of review, modification, and redesign before investing in the final metal tools themselves. For all of these applications, the new HT-90 offers some great benefits. The 90 degrees C HDT makes it suitable for most thermoplastics with an operating melt temperature of between 140 and 200 degrees C. This includes polycarbonate, polypropylene, ABS, acrylic, PVC, and more. The elongation before break of between 4 and 9% gives you the flexibility to bolt the mold tools securely into place and also remove the final injected parts without breaking the tool. The fine feature definition over 1.1 billion drops per cubic inch of part volume allows for the creation of even the smallest details, and similar to the thermoforming, the melt-away support and 3D Sprint software allows you to create porous lattice structures and air venting holes. In this nice example, we have polypropylene that was injected at 176 degrees C at 250 psi barrel pressure and 1800 psi core pressure. 25 molds were created. That's 4 sets per print tray. Each mold succeeded with 10 to 15 injected parts, and in total, 400 parts were manufactured in just 75 hours. Now that's a significant time and cost advantage compared to the traditional molds that would take weeks to produce and would typically cost thousands. Typically in sheet metal forming, a laser or water jet is used to cut out the flat die pattern, and the flat pattern is then bent and formed into the final desired shape. One of the main uses for 3D printing is in the creation of embossed or formed features in the sheet metal die. Such features are typically complex and unique, and therefore no general machine exists for such needs. Our tests show that a 2-inch thick flat part of armor material, one of the original engineering materials mentioned earlier, can be subjected to between 10 and 15 tons of force numerous times without fracturing. The mold would always return to its true shape and could continue to be reused. The transparency of the armor material and the ability to add screw threads to the design all assist in aligning and mounting the parts correctly, saving time and material. Another great benefit is to use the soluble support and infill structures to add part labeling and instructions on these tools themselves. Equally applicable to thermoforming and injection molding tools too. In this example, 3 VisiJet armor tools were used to make 300 parts between the jaws of these aluminium plates in a hydraulic press. No degradation to part quality was experienced during the process, and the entire die development process can be turned around within a few short hours, saving time and money compared to traditional tooling. In this last example, let's look at the room temperature vulcanization or silicon molding process. There are three general methods that 3D printing can be applied to here. Method 1, you replace the silicon mold process altogether with a 3D printed eggshell mold. This replaces an 8-step traditional process with a 2-step process. Example in the top photo here, using the HT-90 material, you can see we've created the eggshell mold and the blue rubber part that comes out of it. Method 2, you replace the 8-step silicon molding process with a 2-step process where you 3D print the actual silicon mold using an elastomer instead of the silicone. For this, you could use the VisiJet black or natural color M2 elastomeric materials that are excellent for printing soft rubber-like parts. And method 3, where you 3D print the master pattern only and then continue with all the regular 7 steps in the traditional silicon molding process. Some examples of these on the far center right photo are here. As in the previous examples, the same properties are advantageous in terms of materials. The combination of surface quality, fidelity, dimensional accuracy, material stiffness, strength, and elongation all work to make any of these methods more timely and cost-effective. In this example in the bottom photograph, we created a functional prototype of a cap that is used to seal one of our own printer heads in our own 3D printers. In this case, a 4-piece mold was printed for around $200 and delivered overnight. This process enabled our own R&D team to trial a true elastomeric part in the machine and tweak the design repeatedly until the rubber-injected part was perfect. The 3D printing process saved weeks, maybe even months of development time and thousands of dollars compared to traditional methods. So there you have it, 4 practical use cases of how MJP-based 3D printing in combination with some of our advanced engineering materials can be used to improve the efficiency and effectiveness of traditional manufacturing processes. And if I could finish with 3 points to take away today, it's these: that MJP technology continues to be the world's most versatile 3D printing for both prototyping and indirect manufacturing, that our material range is continually expanding and improving more and more into the realms of high temperature and functional engineering performance, and that the application of MJP 3D printing can, at the end of the day, save you weeks and months of product development time. It can improve your final product outcome and deliver cost savings of tens or even hundreds of thousands across multiple departments, whether it's design, engineering, or production manufacturing. And of course, MJP technology and the MJP 2500 Plus system based on it are part of a much wider additive manufacturing portfolio offered by 3D Systems. I'm hoping you'll find out more about 3D Systems. Book a meeting with our friendly staff, visit us at our facilities, or just browse our website. Thanks very much and enjoy the rest of your day.